Hello, welcome to the course on advanced electric drives. To do this course, you should have some basic background about electrical machines and some background about mathematics, which is expected in the first year and second year level of an electrical engineering course. Now, before I start, let me just highlight the main objective of this particular course. You must have done a first course in electric machines. So, in that course you have some basic idea about DC machines, AC machines, transformer and various other machines also. Now, in this particular course we will be only concentrating on rotating machines. And we will also concentrate on basically the modeling and control of rotating machines. Rotating electrical machines. Now, before I start about this particular course, let's try to have an overview of the syllabus of this course. This course will start with a generalized theory of electric machines, which is basically done to understand the theory of electrical machine in a common framework. So, the first aspect of this particular course is to know about the generalized theory of electric machines. Now, by generalized theory we mean we have a theory which can be used to analyze various types of machine in a common framework. We know that we have DC machines, we have AC machines. DC machine we may have shunt machine, series DC machine, compound machine. Similarly, in AC machine we may have induction machine, synchronous machine, reluctance machine. So, we have so many types of machines. So, can we understand this machine in a common framework? Can we develop a common framework for all these machines? So, that is done using generalized theory of electric machines. And under this we will be discussing about the modeling aspect. This will also help us to model. Modeling aspect is one of the very important aspects of electrical machine simulation. So, in this case we will be talking about the modeling of DC machines. It is the most easiest machine to model, and then we will be also discussing about the modeling of induction machines, primarily the three-phase induction machines. And then about the synchronous machines. Now, remember that when we want to control the machine, we have to understand the behavior of the machine, and modeling will help us understand the behavior of the machine, and we can simulate it in a computer. We can also develop some control principle based on the machine model. So, the generalized theory will help us develop the machine model which can be used for advanced control of electric machines. So, this is the first part of the course, that is the generalized theory of electric machines. Now, after we finish this, we'll be talking about the reference frame theory. Reference frame theory. Now, in the reference frame theory, we'll be talking about the various types of reference frames we have, and which are very useful to understand the control aspect of the electrical machines. So, for example, if you talk about electrical motors, we know that the DC motors, AC motors are constructionally different. But if you understand the principle of torque production in DC motor, it will not be very difficult to understand the principle of torque production in a AC motor or an induction motor. But to analyze an induction motor just like a DC motor, you have to take a very special reference frame. So the reference frame will help us analyze the machine from a perspective of control. So this is the second aspect of this particular course, that the reference frame theory. And then this will set the background for the advanced control of electrical machines, mainly the rotating machines. And this course will be primarily be focused on the control of AC machines, because the DC machines is the scope of the course which is a fundamental of electric drives. This is on advanced electric drives. So this will be only focusing on the control of AC machines. So we will be taking the control of induction machine subsequently. Control of induction machine, we call this induction machine as IM. So this is a control of induction machine, and under this we start with a scalar control, which is basically the control of the speed and the torque by controlling the frequency and the voltage. So under this we'll have the scalar control, which is the control of mere amplitude and voltage without any reference to phase angle. So this is a simple control which is very good in steady state, but this has some problem in the transient condition. So one of the objectives of controlling AC motors is to have faster dynamic torque and speed response. Whenever we have a drive, the objective is that we should have a very fast control. We should be able to control the torque with a fast dynamic response. Now the scalar control will give the response which is good in steady state condition, but under the transient condition the response may not be desirable. There may be sluggish response in the transient condition. So to have good transient response also, we'll go for vector control. The vector control of induction machine or induction motor, especially a control similar to that of a separately excited fully compensated DC machine. We know that in case of a DC machine we have a separate brass and the field axis. We have armature and we have field. So we can control the current of the armature and current of the field to have independent control, and the field and the armature are orthogonal to each other to ensure good dynamic response. So we will have something similar in case of induction machine when we talk about vector control. And then we will have some advanced control aspect like sensorless control. Now in this case we will be talking about the speed sensorless control. It is seen that in industrial drive, having a speed encoder or having a speed sensor is not always good for the overall robustness of the drive. The robustness reduces whenever you have a speed sensor. So can we have a drive without a speed sensor? Can we have a sensorless drive? It means can we have a drive without a speed encoder? And this will increase the robustness of the drive, and that's why we will talk about sensorless control. And for the sensorless control we have to estimate the speed, we have to observe the speed from the terminal variables like voltage and currents. This will be taking up in the topic under control of induction machine. And then we have some advanced control of induction machines like direct torque and flux control. Now this actually is a advanced control which was patented by Asia Brown Boveri, ABB, way back sometimes in early 90s. Now this way of control aims at controlling the torque and the flux of an induction machine directly using hysteresis control. So the implementation is quite simple. You can have hysteresis control for the torque and flux, and you can control the torque and flux independently as we do in case of a DC machine. This actually finishes the control aspect of induction machine, and then we will be talking about the control aspect of synchronous machine. So under this synchronous motor control, we have something similar to that we have already discussed in induction machine. In a synchronous machine, what we have, we can have a self-controlled synchronous motor control. We know that in a synchronous machine, the rotor should always run at synchronous speed, which is the speed of the rotating MMF. Now, in the transient condition, there is always an instability. Whenever the load changes or whenever the stator frequency changes, there is a tendency of the rotor to hunt around the mean position. That is called hunting, and hunting is a type of instability. So, if you suddenly change the torque or if you suddenly increase the supply frequency, there is a possibility that the drive may become unstable. Now, we are talking about drive, we are talking about electric motor, and in motor we have to have continuous speed variation. The speed should start very smoothly from the rest to the rated value. Even we can also have reversible speed operation. Now, under this condition, it is not possible to supply the synchronous motor from a constant frequency source. Now, when the frequency is variable, the rotor speed is also variable, and the rotor speed decides the stator frequency. It means the rotor always rotates at synchronous speed, which is variable, and the synchronous speed is decided by the rotor frequency. This is called a self-controlled machine. It means the machine is controlling itself. So, this avoids the instability as found in a normal conventional synchronous motor, that is the self-controlled synchronous motor. Now, we will have some advanced feature in this. A self-controlled synchronous motor can also be a vector controlled synchronous motor, where the control aims at high transient torque and speed response, just like a DC machine. So, we will be discussing on vector control of synchronous motor after we have finished self-controlled synchronous motor. And the synchronous motors are basically used for very limited application. They are not very widely used in industry. Majority of the motors used in industry are induction motors. Induction motors are called the workhorse of industry. Now, the synchronous motors are limited to very high power and low speed application. Sometimes at a very high power range, ranging from a few megawatts to a few tens of megawatts. For example, synchronous motors can be used in a drive like steel rolling mill, cement kiln, very low speed but huge. Cement kiln can be rotating as low as 15 RPM, and the rating of the cement kiln can be as high as few tens of megawatts. Mine winders, very large drive but low speed. So, these are basically typical application of synchronous machine. Now, when we talk about the synchronous machine control, we will also be talking about this kind of application, and one of these applications is cycloconverter fed synchronous motor drive. Cycloconverter fed synchronous motor drive. Cycloconverters are naturally commutated. They have SCRs or thyristors. They are very, very robust. There is no commutation circuit. They are line commutated or naturally commutated, and they can be rated for megawatt range without any problem. So, when we have a combination of cycloconverter and synchronous motor, the complete drive can be configured for very high power and low speed drive, because output of a cycloconverter is a low frequency output, and hence the drive speed is low. The frequency output is low and the speed of the drive is low. And then we will be discussing something on control of synchronous reluctance motor. the synchronous reluctance motors are used for applications where there is a need of low rotor weight. The rotor winding here, there is no rotor winding. The rotor is a salient pole rotor. The rotor inertia is very low, and hence the rotor can have higher speed response. The acceleration and the deceleration of the rotor can be very fast. So when there is a need of having a low weight drive at high power application, we can go for synchronous reluctance motor. The stator construction is of course similar to a conventional synchronous motor. The rotor construction does not have any winding, and the torque is only produced based on the saliency of the motor, and hence this is called synchronous reluctance motor. And then we will be discussing something on very special drive, control aspect of very special drives like permanent magnet synchronous motor, which are used for automobile application, for electric vehicles. This has got very high torque to weight ratio because the rotor is a permanent magnet, doesn't have any winding there. We can have very high energy density. We have a special type of drive used for low to medium power application. They are known as brushless DC motors. They are also synchronous motors. These brushless DC motors we call them BLDC, brushless DC motor, BLDCM, and they are used for low power application and as well as medium power application. For example, if you talk about any computer drives, computer disk drives, they should not be having brushes. One of the drawbacks of DC motors is that there is commutator and brushes, and it's a mechanical contact, it's a friction contact which creates a problem very often. It cannot be operated in an environment full of dust. So the DC motors are not very robust, but the brushless DC motors, they just like a synchronous motor. We have permanent magnet on the rotor, and there is a closed loop feedback, and the motor behavior is just like a DC motor. Since we don't have any brush and commutators here, these drives are known as brushless DC motor drives, which are used for low power application like computer peripherals, computer power supplies, as well as medium power applications in some vehicles, automobiles, electric vehicles, and so on. We also have another special type of motor called switched reluctance motor. This is abbreviated as SRM. The switched reluctance motor is supposed to be a good motor, is something like a competitor of induction motors. In this case, the rotor and the stator, both the structures have saliency. The rotor is a salient structure having no windings, just having slots and teeth. The stator is also a salient structure having slot and teeth, and the stator has got concentric winding as opposed to distributed winding in case of normal induction motor or synchronous motor. But in this case, the stator currents have to be switched in conjunction with the rotor position so that the torque is maximized. And since the rotor currents are switched using a converter, this type of motors are called switched reluctance motors. They are used for those applications where there is a need of low weight because the rotor doesn't carry any winding. It is very, very robust, and the robustness is comparable to that of induction motors, and the torque is also sometimes comparable to that of induction motors. So these motors in a limited way could be a competitor to induction motor in a few applications. But the drawback of this type of motors is higher torque ripples. So we will be discussing about these motors at the end. So this is actually roughly about the syllabus of the course on advanced electric drives. Now before we go to the various aspects of the drive system, let us talk about the generalized theory of rotating machine. What do you understand by generalized theory of rotating machine? So what we are trying to do is that we have so many types of machines and we are trying to bring all these machines into a common framework. So what are the type of machines? Now we have the rotating machines, and these are the types of machines we have. We have DC machines. And what are the types of DC machines we have? We have DC series machine, and then we have DC sound machines, which also have their own application, and then we have compound machines where both series and sound windings are present. All right. So these series, sound, and compound machines have their own applications. So these are three types of DC machines we have. And then we have AC machines. And under the AC machines, we have primarily very popularly used two types of machines. One is an induction machines. We call this to be IM. And then we have synchronous machine, SM. Okay. Apart from these two types of machines, which almost contribute to about 70 to 80% of the drive, maybe about 85% of the drive system, remaining 15% would be coming under special machine. So we have two types of induced EMF. One is a statically induced EMF and the other one is rotationally or dynamically induced EMF. So let's try to understand the differences between the two types of induced EMF which are commonly encountered in a rotating machine. So let's try to understand this, having two coils, one in the stator and other in the rotor. We have a rotor here and we have two axes, and we have a coil in the D axis stator. This we call as capital DS, and we have a coil in the D axis rotor. This we call as capital DR. And these two coils are magnetically coupled. Naturally, when the two coils are aligned, there will be maximum coupling. So these two coils are maximally coupled, and we can have a dot convention. So this is our dot here, and this is also the dot here. So this terminal is corresponding to this terminal of the stator. And what we do here, this is our D axis and this is Q axis. D stands for the direct axis, Q stands for the quadrature axis. And we define an inductance called MD. MD is the mutual inductance between DS winding and DR winding when they are aligned. When the two windings are aligned, let us say that the mutual inductance is MD. So this inductance between these two is capital M subscript D. Now what we do here is that in the D axis stator we inject a current, and this current is a time varying current. Okay. So maybe we have a current source here, we can have a current source in this case, and this current is injected into the D axis stator, and the current is IDS. And what is the nature of this current? This current is given as Im cos omega t. So it's a time varying current, it's a function of time, and it is given as Im cos omega t. This structure is a rotor. This is free to rotate, and this one is in the stator. And when this is having this current Im cos omega t, what about the flux linkage? We are finding out the flux linkage lambda dr, the flux linkage with d axis rotor, that is winding dr, that's equal to, the rotor is not carrying any current, rotor is open circuited. So we are finding out the flux linkage in the rotor due to the d axis stator current, and this flux linkage is given as Md. Md is the mutual inductance between the rotor and the stator when they are aligned, and the current in the stator is Ids. So Md into Ids, and that's equal to, what is Ids? Ids is Im cos omega t. So we can say that Md into Im cos omega t is the flux linkage with the d axis rotor because of the current in the d axis stator. So now what happens here is that we give the rotor a motion. The rotor is rotated now, it is not stationary, it is free to rotate, and it rotates at the speed of omega r. So when the rotor rotates, the flux linkage will change. The flux linkage lambda dr is the flux linkage when they are aligned. So we can say that this is for theta r equal to 0. Theta r is the rotor angle. The angle between the rotor and the d axis stator is theta r. Now when it is rotated, what happens? This is given a motion. So if this is given a motion and the speed equal to omega r, what happens? Let me draw another picture here. This is the rotor, the center of the rotor, and then we have the d axis stator is excited with a current source, and this current, this is the ds winding, and Ids is given as Im cos omega t. So this is the d axis, and this is the q axis. And the rotor is now rotating. After some time, this is rotating in the clockwise direction, omega r, speed is omega r here. The winding which was aligned with the stator at t equal to 0 has now moved to a different position. Now if I see the new position of the rotor winding, the new position will be somewhere here. So this is dr, this is the winding, that is dr. Now the dr axis is this. Now this angle between the d axis stator and the rotor winding is now known as theta r. Now if we want to find out the flux linkage in the d axis rotor or dr winding rotor due to the stator current, which is Ids, that's equal to Im sin omega t, we can write down the flux linkage as follows. The flux linkage in the winding dr due to the stator current is given as Md Ids. Now the rotor has moved through an angle, that is theta r, into cos of theta r. So this is the flux linkage with the winding, that is dr, and the dr winding is now rotating at a speed of omega r. Now if I want to find out the induced EMF in the rotor, suppose I have a voltmeter here, I can connect a voltmeter here, and I can measure the induced EMF by having a voltmeter. So if I have a voltmeter to find out the induced EMF, the induced EMF E dr, as per the Faraday's law, this will be given as minus d by dt of lambda dr. The rate of change of flux linkage, and the negative side is due to the Lenz's law. Now I have to differentiate this lambda dr to find out the total induced EMF. Now what is my lambda dr? Lambda dr is given as Md Im cos omega t into cos of theta r. So this is also a function of time. Lambda dr is also a function of time. It's also a function of position, and the position is also constantly changing. Theta r, the rotor angle, this angle is not constant, it is constantly changing. So if I differentiate this with respect to time, what I have here is the following, that this will be a differentiation by parts. So minus of md ids d by dt of cos theta r. I will first differentiate the cos theta r, and then I will differentiate md cos theta r d by dt of ids. So this is the induced EMF. Now if I differentiate cos theta r, it will be minus of sin theta r into d theta r by dt. And if I differentiate ids with respect to time, ids is Im cos omega t, it will be Im sin omega t with a negative sign into omega. So let me just try to write down the result of this. So if I differentiate this and simplify, what I will have is the following. I will have md Im omega r cos omega t into sin theta r plus md Im omega cos theta r into sin omega t. So this is the expression for the induced EMF. Now I can express again sin theta r in terms of cos theta r, sin omega t in terms of cos omega t. So if I do that, I will have the final expression md Im omega r cos omega t into sin theta r is cos theta r minus pi by 2. I can replace this sin theta r by cos theta r minus pi by 2. Similarly, I can also replace sin theta r by cos omega t minus pi by 2. So I can just write down here md Im omega cos theta r into cos omega t minus pi by 2. So this is a very interesting equation. It's an interesting expression in the sense that the induced EMF, which we know that it is equal to minus d lambda by dt, has got two different terms. The first term, you can see that this is actually a function of speed. So this is a function of speed. If speed is equal to 0, this term will be equal to 0. So we would like to call this as the rotationally induced EMF, or EDR rot. It is called the rotational induced EMF or dynamically induced EMF. This is basically coming up due to the motion. So this is called a rotationally induced EMF. And the second term, which is given here, is called the statically induced EMF, or EDR stat. Now if you see, this is interesting to note that the rotationally induced EMF is a function of omega r. It means if the speed is equal to 0, the rotationally induced EMF will be equal to 0. So that EMF is coming because of the rotation. The statically induced EMF is a function of the frequency. Omega here, if you see this omega is the electrical frequency of the current. If the frequency of the applied current is equal to 0, this component will be equal to 0. So this is the statically induced EMF, because this is induced because of the coupling between the rotor and the stator. Furthermore, you will see that there is another interesting feature between the two EMFs. You can see that the rotationally induced EMF is in the same time phase, because our time phase angle is cos omega t. Omega t is the phase angle here. Cos omega t is the phase angle or the phase of the time. So you can see here the rotationally induced EMF is in the same time phase. it is also cos omega t. This is also a function of time, and it is cos omega t. So, it is in the same time phase, but it is pi by 2 lagging behind the space phase. It is cos theta r minus pi by 2, and the statically induced EMF is in the same space phase, because this is cos theta r. Theta r is this angle. So, this will be maximum when these two windings are aligned. So, whenever theta r is equal to 0, it means this winding is aligned along this. You have maximum statically induced EMF, the coupling will be maximum, the induced EMF will be maximum. And if theta r is pi by 2, when this winding is along the q axis, the statically induced EMF will be 0. So, the statically induced EMF will be in the same space phase, but pi by 2 lagging in the time phase. You can see here also we have expression of time, it is cos of omega t minus pi by 2. So, I summarize here that if you talk about the statically induced EMF, this is in the same space phase. It means the statically induced EMF will be maximum whenever two coils are aligned along each other. The axes of the two coils are aligned, then only we will have maximum coupling, then only we will have maximum statically induced EMF. So, if I have a winding here, if the other winding is also having the same axis, I will have the maximum coupling, and hence I will have maximum statically induced EMF. This is in the same space phase, but pi by 2 lagging in time phase. Although the second coil here will have the same space phase with respect to this, if I connect a voltmeter here and measure the induced EMF here because of a current variation in the first coil, and that is Im cos omega t, this induced EMF will be lagging behind this flux, by pi by 2. Whenever I have a current, I will have a flux production, and this induced EMF will be lagging behind the flux in time by pi by 2. So, this is an important aspect of statically induced EMF. Now, if you talk about the dynamically induced EMF or rotationally induced EMF, dynamically or rotationally induced EMF, now this will be maximum when the two coils are in quadrature. It means if I have one coil here and this coil is being excited by a current, and if I have other coil and the two axes are orthogonal to each other, this axis is here and this axis is right angle to this axis, then I will have maximum rotationally induced EMF. Here the coupling is 0, but the rate of change of flux linkage is maximum due to rotation. So, we can say that in the same time phase, if I have, this is Im cos omega t, this induced EMF with the rotationally induced EMF, the component of that induced EMF which is called the rotationally induced EMF, that will be in the same time phase as cos omega t, but it will be shifted in space by pi by 2, but pi by 2 lagging in space phase. This is a very important conclusion. It means a coil which is right angle to the other coil will have maximum rotational induced EMF, and that is the reason why in case of DC machine you have seen that the Bros axis is orthogonal to the field axis. They are not in the same axis. The Bros axis and the field axis are orthogonal. If you align the Bros axis with the field axis, the rotational induced EMF will be equal to 0, because in a DC machine we have only rotational induced EMF. The field winding is not having any alternating current. So, in a DC machine, if you have seen that we have a DC machine structure, we have the Bros here and we have the field winding here. This is the field winding. and this is my armature. And whenever I have perpendicular relationship between the two coils, I may have a hypothetical coil here because the brushes are in the q axis. So this axis is orthogonal to this axis, and the brush will have the maximum rotationally induced EMF. And that is the induced EMF in case of a DC machine, and that's the reason why in case of DC machine the brush axis and the field axis are orthogonal to each other. Now, after having said this, we are now talking about the generalized theory of electric machine, and we know that we have two different types of induced EMF. One is the statically induced EMF, and the other one is the rotational induced EMF or dynamically induced EMF. And again, we have also seen that in generalized machine we are talking about a two-axis model. Suppose we have a rotor here, and we have the stator. This is the rotor, and this is my stator. So I have two axes. This is my D axis or the direct axis, and this is the quadrature axis. So I will have two different axes, and I will have only two sets of coils. One set of coil in the D axis. D axis stator, we can call this to be DS. A stands for the stator, D stands for D axis. Similarly, in the D axis rotor, I will have D for the D axis, R for the rotor. So I have one coil or the one winding in the D axis stator and one winding in the D axis rotor. Similarly, I have other winding in the Q axis stator. I call this to be the winding QS, and I have other winding in the Q axis rotor. I will call this to be winding QR. Okay, and this winding is coupled with this winding. So I show it by a dot convention. This winding is coupled with this winding, and similarly in the Q axis also this winding is coupled with this winding. So this thing, the Q axis is coupled with Q axis and the D axis is coupled with D axis, and then the rotor is rotating in the clockwise direction. This is my direction of rotation, and the speed is omega r. Now this is the generalized machine that we are talking about, and this was given, the concept was given by a scientist called Kron, and this is called the Kron primitive machine. Kron primitive machine. So I have two axes. I have one stator, one rotor in the D axis, one stator and one rotor in the Q axis, and the D axis is coupled with D axis, and this D axis is stationary, is fixed. Q axis is also fixed. The Q axis stator is coupled with the Q axis rotor, and it is rotating in the clockwise direction. So we will be discussing the remaining part in the next lecture.